Good morning, learners. It's my privilege again this morning to help you in finalize your preparation for your physical science paper 1 on Friday, and I trust that you are well on your way in your preparations. So this is just an attempt to just highlight the important information for each topic, and maybe remind you to be aware of certain common mistakes that learners do every year. So I'm going to start off where I end off in our previous session, and I'm going to start off with the Doppler effect and some common mistakes and key issues on the Doppler effect. Right, let's go to the first important thing on the Doppler effect is a definition, and I want to remind you on the importance again on definitions. If you look on the screen, you will see that there are two very important words in the definition of the Doppler effect, and the first word is the change in frequency. Very important change in frequency. And then also the second mark is on the fact that the listener and the source has different velocities relative to each other. Right. I trust everything is on the screen at this stage. Okay. Right. So again, emphasizing the common error is the fact that learners omit the change in the frequency and the word relative. There are two ways of stating that last part. Like in your definitions given in your guideline, stated like here that the source and the listener have different velocities relative to the medium of sound propagation. You can also state that the sound source and the medium have relative velocities to each other. I just want to confirm that we are on the screen for my manager. Thank you very much. Right, then the next thing in general also, the sloppiness, if I can state it like that, many times in phrasing your definitions. You sometimes get learners that use the word change in sound instead of change in frequency, or the sound emitted by the listener, or instead of by the source. So please make sure that you are accurate in your definitions, and that you concentrate in the exam to use the correct wording for the definitions. Learners sometimes wrongly are given an explanation for the Doppler effect and not a definition. An explanation is where learners give the two scenarios, stating that in case the source is moving away from the listener, there's a decrease in the frequency, observed frequency, and when the source is moving nearer, there's an increase in the observed frequency. That is explanation. That is not a definition, so no marks for that. So please give the definition. And then on calculations of the Doppler effect, and I'm going to repeat it a few times in this lecture. Please read carefully, read properly, understand the scenario, understand and interpret the data given to you properly before you start attempting the problem and selecting a formula, etc. Right, just an example from a previous paper, and you will, I think it is the final exam of 2018, if I'm correct, that the learners don't interpret the data correctly. It was given to the learners that the listener detects a frequency of 50 Hertz lower than the source. Firstly, you can relate this, you must relate this to the fact that the listener is moving away from the source, the fact that the frequency he detects is 50 hertz lower, and learners haven't seen that, and then they only see the value of 50 hertz and only interpret that as, say for instance, the frequency detected by the listener, or the frequency sent out by the source, instead of reading and interpreting as a 50 hertz lower. So please read carefully. Now, the Doppler equation, sometimes if the learner just read the question and they know it's a Doppler, about Doppler effect, and they just write down the Doppler equation, forgetting that the wave equation is also a relevant formula in the Doppler effect, giving you a relationship between the sound, the velocity of the sound, the wavelength of the sound, and the frequency of the sound. So please don't forget about this formula. Sometimes they give you the wavelength of the sound emitted by the source, and then you at first must calculate the frequency emitted of the sound emitted by the source. And remember this, the sound the speed of sound in light will be given in the question or on your data sheet. So that is a constant value given to you, so therefore you can calculate the frequency if the wavelength is given to you. Then learners are sometimes struggle to see if this is a case where you must use simultaneous equations or not. And simultaneous equations, to solve the Doppler question with simultaneous equations, is only where there is two different scenarios, where the frequency detected by listener is given for two different scenarios. So then you have two different equations for the Doppler effect, and then it is certainly a case of simultaneous equation solution. The other mistake that learners do is that they only see two values or frequencies, and instead of seeing this as two frequencies detected by the listener, they just interpret the two frequencies as the one for FL and another one for FS, and they just take it as a single step calculation, and they haven't understand the question properly, that is two different scenarios given, so therefore it is simultaneous equations. Right. Note please, start off with the Doppler equation as given on the data sheet. If you start off with the derived formula, you interpret now the source is moving towards the listener, and you interpret, derive that formula from the initial formula on the data sheet, and you make a mistake, you lose that mark. So always start off with the Doppler equation as given on the data sheet, and then you can start deciding if it is V minus VF, Vs or V plus Vs in your equation. Start off with the initial equation. Now, frequency of the source is sometimes not given directly to you, but by means of giving the wavelength of the sound emitted by the source. So then just to remind you, please remember the use of this wave equation. Also, sometimes the frequency, and you know, they must get to a variation of questions, and the last few papers, the variation and in the question, and maybe also a way of raising the level of difficulty of the Doppler equation, the problems using Doppler equation, they sort of put the difficulty in the way they present the frequency, and they, in the last few papers, there was instances where they make use of a graph of air pressure against time. So now you must realize that you must make use of the formula F equals 1 over, let me just go back, 1 over T, and then you must realize what is one complete wavelength, or how many wavelengths is indicated in this diagram. And in this diagram you must be able, in this graph, you must be able to identify that there are sorry, just go back, that there are actually, just get my mouse here, that there are there are two complete waves. So this is 2 waves per time. So the number of waves is 2 divided by the time. The time is indicated 16 times 10 to the power minus 4. So the frequency equals 2 divided by 16 times 10 to the minus 4. If you only have decided to make use of one wavelength, and then the period of the wave, so the time taken for one wavelength, then you halve that time given, so then it will be 1 divided by 8 times 10 to the power minus 4. So remember then that you can make use of F equals 1 over T, or if you chooses more than one wavelength, it is 2 divided by the time taken for those 2 wavelengths. Right, that then concludes my comments on the Doppler effect, and I move on to Coulomb's law, and I'm just going to get it here on the screen. I'll start from the beginning. Right, let me just see here. Right, it is Coulomb's law, and I must just get a full screen here. Anyway, let me just see here. Okay. Right, I'll think I'll move on in this way. I hope it is clear to you. Let me just see if I can get a full screen. I don't want to. Right, okay. Let us move on with then Coulomb's law and electric field. So first, Coulomb's law. Now, in every topic, a definition are going to be part of the question. Every question will have a definition as part of the question. Now, in your paper, normally it's question 7 on Coulomb's law, and one of the laws that can be asked on Coulomb's law and electric fields is law, and the mistake readily or many times made by the learners is the words proportional. The electrostatic force between two point charges is proportional to the product. Remember, it's proportional to the product of, and then the charges. And remember, you mustn't confuse it with Newton's gravitational law, universal gravitational law, where it is compared to the masses, so that the force is proportional to the product of the masses. That is Newton's universal gravitational law. So be aware of that. Coulomb's law stating it's a product of proportional to the product of the charges. The safest way to end the last part, the safest way is to state it that this force is inversely proportional to the square of the distance between their centers. then it doesn't matter if it is a sphere or a particle, a particle. So because in a square, in a sphere, you can't use the term the distance between the two spheres or objects. You must then use the term the square of the distance between their centers. If it is a definition relating to 2-point charges, it isn't necessary to state the distance between the square of the distance between the centers. So my suggestion then is that you always, in Coulomb's law, for the last part, use the word the square of the distance, and then important, between their centers. Then you are safe for either a sphere or a particle. The definition, you won't be penalized for that. Then field patterns are also one of the questions asked, and normally it's a question that is asked of, it's a level 2 question, so it's a question that is supposed to help the learner at least to get some marks. Now, many a times learners lose marks unnecessarily because of the shape that is really inaccurate. It is a more or less shape. It can't be a more or less shape. It must be really make sure that you are accurate on your shape, especially the shape between two positive test charges or two negative charges. That shape is difficult to draw. So go back and have a look on that diagram on those shapes, and make sure that you know, even for the electric field pattern between a positive and a negative. So make sure that you are accurate on the shape. Make sure that your field lines touch your sphere, and also that the field lines is not moving. If you draw a sphere, that is not crossing that outer line of the sphere, moving into the sphere. That's important. There's no electric fields inside that sphere, so just touching the sphere, and also then the direction. Remember, it is always from the positive charged object to the negative charged object. So the direction, that is where you get your marks. 1 mark for shape, 1 mark for things like touching the sphere, field lines not crossing, and the last mark for the direction, positive to negative. Now, the principle of conservation of charges is often asked, and you must use it to get a net charge on each sphere after 2 charged spheres that were touching each other and then removed again from each other, and now you must calculate the net charge on each sphere. So the principle of conservation of charges states that the total charge of the 2 separate spheres, if you add that before touching, must be equal to the total charge of the 2 spheres after touching if you add this together. So Q total before touching must be equal to Q total after touching. Now, how do you apply it in a calculation? Now, if you have, for example, 3 spheres, and before touching, you can get the total of the charge of the 3 spheres by adding, say for instance, 3 Coulomb plus minus 1 Coulomb plus 4 Coulomb. Then you get the total charge or the net charge before touching, and then you know after the spheres have been touched that total of the charge of the three spheres must be the same. So it must be after touching Q1 plus Q2 plus Q3 also. But now they have given you three identical spheres, and that's very important. I can ask only the question if they have given you identical spheres. So now you just divide that total charge before touching, you divide this by 3, and now you get the charge or the net charge on each separate sphere. And remember, the charge on each sphere after touching is the same charge. It will be for all three charges, all three spheres, plus 2 Coulomb, or it will be for all three spheres minus 2 Coulomb. But each sphere, because it's identical spheres, has the same value for the charge. Very important. Right. Now, many times in a multi-step question, normally it is a scenario of the three charges given, and then they touch, and then you must remember now, from there on you must work with the new values for Q1, Q2 and Q3. And the typical question that can be asked of you is to calculate the net force that two of the charges exert on one specific charge. Now the easy example is where the three charges are in a linear to each other, and so then it is easy that you just calculate by means of Coulomb's law the force that each of the two spheres exert on the third sphere, and then you must, by means of a force diagram, decide if you must subtract or add the two charges to get the net charge. I'm going to have a look on a scenario where you have where you have three charges, but they are at right angles to each other. You will see here Q1, and then it's a Q2, and then there is a Q3. So they are at right angles to each other. And now the question is, you must calculate the net force that Q2 and Q3 exert on Q1. And now I've given to you, I've indicated to you if the charge is positive or negative. So Q1 is positive, Q2 and is negative, and Q3 is positive. That is very important to know the charges of the spheres, if it's positive or negative. Now, what you are going to do, you are going to apply Coulomb's law to calculate the force between Q1 and Q2. And also you apply Coulomb's law to calculate the force, electrostatic force between Q1 and Q3. In every calculation for F net using Coulomb's law, when three charges are given, if it's linear or at right angles, you must first draw a force diagram. In physics, a force diagram is very, very important, also in this instance. So now you will see, if you look at the force that Q2 exerts on Q1, Q2 are negative, Q1 is positive. So Q2 will exert a force to the right on Q1. So therefore, in my force diagram, I indicate that the force of 2 on 1 is to the right. And then Q1 is positive, Q3 is positive, so Q3 will exert a force on Q1 in an upward direction. Therefore, in my force diagram, this is then F3 on 1 is then in a vertical position. So here now is my force diagram. But now there's a very, very important next step in this calculation, and that is that you must draw a vector triangle. Why a vector triangle? That is because you need a vector triangle to solve for F net. And you will realize and you will tell me you must use Pythagoras and your trigonometry to calculate the magnitude firstly of F net, and also secondly the direction of F net. Now I've converted my force diagram into a vector triangle, and I've used the principle of the head to tail, putting the vectors head to tail. So for instance here I've used F31 indicated there, and then I take F21 and I put it to the head of the first vector, and then I close my triangle by completing the vector, the force for F net. So head to tail, F31, F21, close my triangle, that indicates F net, and now I have a vector triangle to use Pythagoras. And now you will know, all know what the Pythagoras indicate to you, that F net, the square of F net equals the square of F31 plus the square of F21. So then you can apply Pythagoras to get the magnitude of F net. And if they ask the direction, you must calculate this angle between F31 and F net. Then you must use logarithmy, and you must use sine or cos, whatever values are given to you. In this instance, you will be able to use both sine or cos function to calculate this angle here, and you can also get the direction. I must say it is quite a few papers back that have asked to calculate the direction. Maybe they think it is too much maths to also ask the direction, but maybe they can, it's time to also ask not only the magnitude using Pythagoras, but also the direction using your sine and cos function. So this is for the calculation of F net. So like I've said, they can ask the example, the scenario can be about three charges, three spheres at right angle to each other, or they can be placed linear. So the only difference, if they place linear, you're not going to get a vector triangle, and you're not going to use Pythagoras. You're only going to add or subtract the two values from each other, looking at your force diagram, and then you get the magnitude and direction. The next page indicates an example where they ask of you to calculate the net force when the three spheres is in a linear position to each other. Here, for instance, now they're going to ask you, like in the previous diagram, the force on Q1. If I ask you the question on Q1, you will see Q2 is attracting Q1 Q1 is attracting Q2 to the left. And if I draw, and maybe I must just go back, okay, and if I must draw my force diagram, you will see F1 on 2. So F1 is applying a force to the left on Q2, therefore my force acting to the left indicated here, and then Q3 is positive, and therefore Q3 will exert a force to the left on Q1. Okay, and therefore now what's the important issue here? Now you see that your two forces are acting in different directions, one to the left and one to the right, and therefore you know you must subtract the two values. After you use Coulomb's law, you use Coulomb's law to calculate the force of Q1 on Q2, and also a second calculation, again Coulomb's law, the force of Q3 exerted on Q2. So two different calculations, and then looking at your force diagram, you realize the two forces on Q2 are acting in different opposite directions, so therefore you must subtract it from each other, and then your final answer, you must interpret your final answer. And how do you do that? You have chosen direction. Say for instance you have stated to the right is positive, and if you now get a negative answer, then you know your direction is to the left. So that negative, say for instance 0.2 newtons, then becomes 0.2 newton to the left. So you must interpret that positive and negative value you get according to the direction you have chosen. And it's very important, if they just ask calculate F net on Q2, they just ask that, you must give both magnitude and direction. If they state only calculate the magnitude on F net, right, then you don't have to indicate the direction, but always be safe, rather give an extra information indicating the direction than leaving it out. It is very important that you don't, in Coulomb's law, and maybe if I just can go back to Coulomb's law on this example here. Using Coulomb's law, substituting Q1 and Q2, you don't, if Q1 is minus 6 nanocoulomb, you don't substitute minus 6 times 10 to the power minus 9. You don't substitute the negative value into Coulomb's law. You just calculate the magnitude of that force, and you use your force diagram to interpret the direction. So no negative values for charges substituted into Coulomb's law. And then just reminding you, the vector diagram determines determines your direction, and by looking at subtracting or adding the two values, and then interpreting your answer. If it's negative, you interpret it according to your convention. If you have said to the right is positive, then if your answer is negative, then your direction will be to the left. Okay. Getting to electric fields, the question often asked, and again, every topic has normally a definition. So I've calculated in the 2019 final exam that 18 marks was for definitions. So you must please know your definitions. The definition for electric field at a point is derived from the formula, or the formula is actually derived from the definition, and that formula is stated that E, electric fields, equals F, electrostatic force, divided by the charge at that certain point. So therefore, the definition of an electric field is therefore the electrostatic force experienced per unit positive charge. So this highlighted phrases or words are the crucial part of the definition. The force experienced per unit positive charge. For each of these words omitted. If you even omit the word per, because that has a definite meaning, that per unit positive charge. For each word omitted in this definition, there's 1 mark subtracted, and therefore if you omit 2 of these keywords, you get 0 for the definition. So unit charge, very important, and the positive charge, because the direction of an electric field is determined by the fact that the definition state it's the force experienced per unit positive charge. So all these words, force experienced per unit positive charge, is very, very important. Please don't confuse this definition with the general definition of what is an electric field. And therefore the question specifically asks the electric field at a point. So you can't describe it as the area where a certain charge experience a force. Firstly, it is an area. The word area then immediately will cause you to get 0 marks, because now you are not describing the electric field at a point. And secondly, you can tell me, but at least there's something about electrostatic force where a charge experiences a force. Isn't that worth any marks? Immediately I will refer you back to the keywords. The force per unit positive charge. And at least all 3 of those words are not part of this definition, so you will get no marks if you describe it in that way. So this is only a general definition or description of what an electric field is. Right, moving on to the calculations of E net. We have calculations using Coulomb's law for calculating F net. And please make sure that you know what the examiner is asking. Is he asking F net or is he asking E net? A lot of mistakes is where E net is asked and learners use Coulomb's law and vice versa. So make sure what is asked of you, F net or E net. Now normally they will give you 2 charges, and according to exam guidelines, now they can only make use of the charges and a certain point linear to each other, charges in a straight line. They can't ask you a question about forces, net electric field at right angles to a certain point. Now it's linear, and therefore firstly always draw a vector diagram to indicate the electric field acting through that point. Now firstly, Q1 is negative, so the direction of electric field is always towards the negative. So I'm moving from the right to the left to charge Q1. So therefore I'm moving through point P to the left to get to Q1. So therefore E1, the electric field caused by Q1 through point P, is to the left. And now this is a positive charge. Q2 is a positive charge. So now electric field lines is from the positive away from a positive charge. So away from Q2, so through point P, I'm moving from Q2 to the right through point P. So therefore electric field through point P is E2, and that is to the right. And now also you must choose a certain direction. You must choose, for example, to the right is positive. And now you calculate the electric field E1 through point P and then E2 through point P. And now you realize, according to my vector diagram, I must subtract the two electric fields from each other to get the magnitude of the net electric field. The direction we will come to in the next point. Just again, very clearly stated here. Please, no negative values substituted into your formula for calculating electric field at a certain point from a charged sphere. You only substitute the positive. If it is minus 3 nanocoulomb, you substitute 3 times 10 to the power minus 9, not minus 3, because a minus 3 in the answer, a minus answer indicate nothing about direction. Direction of the net electric field is only determined by your force diagram and the addition of the subtraction of your values. Nothing about the values that you substitute. Now you calculate your two electric fields E1 and E2, so both will be initially positive answers. And now you go and have a look on what your vector diagram is indicating to you, and then you decide what you must do. Must I add or must I subtract? And then you interpret that answer. If you get a negative and we have decided to the right is positive, then you know your final answer. You give the magnitude of E net and then state it to the left. So direction is decided by interpreting your answer according to the direction you have chosen. Very important for both calculations of F net and E net. And I want to emphasize that you really distinguish. Many a times question 7 is divided. The first part is on Coulomb's law and calculating F net, and then they go into the next part of question 7, say 7.3, and then they go to a second scenario, and then they ask E net, and learners get confused between when they must calculate E net and when F net. So make very sure that you know what you are busy with. Right, just make sure, and I've touched on it earlier, just make sure where a scenario is given, where three spheres are given, and then they touch, that you work with the new values of the spheres after touching, that you don't work with the initial values of the spheres. And remember, when it's necessary if the question is about a point charge that is an electron or a certain number of electrons on that point charge, remember that the mass and the charge is on your data sheet. The charge of an electron 1,6 times 10 to the power minus 19. So remember, it's on your data sheet. They don't have to supply that information to you. Right, we just take a quick break. Right, welcome back. I'm going to start off now with electrical circuits and general mistakes and some hints on electrical circuits and Ohm's law. Normally, like I said, normally in the paper is question 8. If they split the two questions on Coulomb's law and electric fields from each other, then it will be question 9. Again, like I've said, definitions, very important for each topic, and one of the definitions will be asked, and Ohm's law is a very important definition, so make sure again that you know it by heart. and this very simple definition that the potential difference across a conductor is directly proportional to the current, and you know if the temperature stays constant. But the relationship in Ohm's law is between potential difference and current. So if we put it in symbols, it is V directly proportional to I if T is constant. Please don't include the relationship with R. The formula derived from Ohm's law is R equals V over I. That is the formula derived. But that is a derived formula. It isn't Ohm's law. You can't state that R is directly proportional to potential difference and indirectly proportional to the current. That is not Ohm's law. That is the formula derived from it. So Ohm's law is only the relationship between V and I as directly proportional at constant temperature. So make sure that you don't make this mistake. Then the second definition that can be asked of you, and normally it causes a lot of problems and a few misconceptions and a few definitions that in the past seems acceptable, but last year that the national examiners clearly indicate that some definitions won't be accepted. So let us start off with the correct definition of what the EMF of a cell or a battery is. And that is very important. It's a maximum energy. Okay, the important word might be energy, but I really prefer that you use this word maximum. That is the maximum energy that a battery can deliver per Coulomb charge or per unit charge. The maximum energy that can be delivered per Coulomb charge. The formula V equals W divided by Q is actually also gives you some guidance to this definition for EMF. The maximum energy per Coulomb or unit charge. Sometimes they want you to indicate to the examiner that you understand this definition for EMF even better, and then they ask you to define an EMF of 12 volt, for instance. Now all that is different now. Now you can state that the EMF of 12 volt now indicates that the battery is giving that maximum energy is now 12 joule of energy per Coulomb charge. 12 joule of energy delivered per Coulomb charge by that cell or battery. So the maximum energy is now just 12 joules per Coulomb charge. Many learners, this question was asked, if I'm not mistaken, in 2018, and I can tell you this was one of the questions. This definition of defining what is an EMF of 12 volt was one of the worst answers questions. So make sure. I have an idea it isn't really in the exam guidelines, but they can ask it as a definition. Now, what is not acceptable, and this is misleading because some maybe textbooks, some notes, etc. Indicates this as a definition of EMF, and that's a potential difference across the poles of a battery in an open circuit, or in the potential difference across the poles of a battery when there's no current flowing. This is actually a description of how you can determine. If somebody give you a cell or a battery and ask you, please tell me what the EMF of this battery is. This is the way how you can determine or measure the EMF. So this is a process of determining the EMF. It's not the definition, and it was clearly stated last year that this definition won't be accepted as a correct definition for EMF. Just a few formulas, maybe The first one is not used often, but I just remind you maybe on the definition of the current charge Q divided by the time. It's the number of coulombs per time. More often used is this formula, and this is actually the formula that helps you to with your formula for EMF. So that the EMF, the voltage often is that voltage, and it indicates the maximum energy or work that the battery can produce per Coulomb charge. So this defines potential difference, but it also relates to the definition of EMF, if this can help you in a way with that definition. And then important, derived from Ohm's law, they've decided that relationship between V and I gives you a good indication of the resistance that a resistor is giving to current that's trying to flow through it. So this is the formula derived from Ohm's law, or the resistance is equal to V divided, the potential difference divided by the current through the conductor. And just a reminder on we're moving to solving circuit diagrams, and you can't solve a circuit diagram, okay, firstly if you don't know your formulas, but the most important aspect on solving circuit diagrams is to know the principles for series, for resistors in series and resistors in parallel. So I just remind you, this is work maybe that you know from grade 9, but very important. Firstly, in series, you know that the current is in all series part of the circuit is equal to each other, and then secondly, that if there are resistors in series, you just add the potential difference across each resistor in series, and then this gives you the total potential difference across that resistors, and if it's only resistors in series in the whole circuit. And then to get the total resistance for resistors that is connected in series, you just add the different resistors, the magnitude, the value of the different resistors to each other to get the total resistance. So a series circuit, very maybe simple, or not so difficult maybe as in parallel, but still very important to know. And now parallel resistors connected in a circuit. Firstly, you must know that if you add the current through each parallel branch, you will get the total current in the circuit. And this value for the current can differ from each other, because the value of the resistors can also differ. So the sum of the current through the branches gives you the total current. And then, very important, that the potential difference across your different resistors in parallel, that say for instance you have a circuit with 3 resistors in parallel, and your external potential difference across the cells is 12, or let's say 11.5 volt, then each of resistor 1, resistor 2 and resistor 3 will get the same amount of the same potential difference across the resistors, namely 11.5 volts. So the resistance across the branches is the same. And now to calculate therefore the parallel resistance, the parallel resistance, so the resistance in total, in net resistance caused by the 3 resistors in parallel, the definition you will know. All this, this definition you must know as the inverse of the parallel resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And remember, the answer you get is 1 over RP, so you must get the inverse value to at the end get to R parallel. So this is the basic concepts that you must know, and really you are a grade 12 learner in physics, and your knowledge of electric circuits, this must be on your fingertips, and you must know how to apply it in a circuit diagram. In a circuit diagram, maybe like in any other question, it's very important that you study that circuit diagram very carefully, that you understand the meaning of each value, that you know if a potential difference is given, that you know to which resistor does that potential difference relate. The current given, is this the total current in a series part of the circuit, or is it the current just in one of the branches? So please don't look at the circuit diagram as a whole. Dissect it into parts so that you understand the meaning of each value, and then you simplify that circuit diagram for yourself before solving the questions. Remember that resistors added in parallel always causes the total resistance to decrease. Resistors added in parallel always causes the total resistance to decrease. And if here you have a graph of potential difference against current, and they've told you that you have two resistors. The one that is in the one circuit, the two resistors is connected in series, and in the second circuit, the two resistors is connected in parallel. Which of this graph indicate the graph for the circuit in which the resistors is connected in parallel. So now you know resistors connected in parallel always decreases the total resistance. So you know, say for instance, two resistors in series of each 2 ohm, then this will be 2 ohm plus 2 ohm in series. So the total resistance for the two in series will be 4 ohm. But if those two resistors is connected are connected in parallel, it is 1 over 2 plus 1 over 2, and it is 1 inverse of 1 stays 1. So in parallel, the total resistance of those two resistors will be 1. So in parallel, the total resistance is always less than the resistance in the series circuit. So now it's very easy to know that graph Y is a graph related to the parallel circuit. Now, internal resistance. I think the chance of you not getting a circuit diagram with internal resistance is very slim. So your circuit diagram will certainly include internal resistance Ri. Now then Ohm's law, and if you rewrite Ohm's law instead of R equals V over I, you can rewrite it as V equals IR. But now if internal resistance is present, then it is rewritten as now the EMF that relates to the potential difference, the total potential difference that we call EMF, equals IR, and R indicates external resistance, and I times small letter r, the internal resistance. So now for internal resistance present in a circuit, this formula is now the formula that you can use as a whole for the circuit. So remember that. This formula is also applicable, and you must be able to use it solving different sub-questions in the circuit diagram. But in general, this is now the question where you can calculate internal resistance or external resistance, etc. Just carefully look at the values given. Now, another formula that is derived from this formula for including internal resistance is the fact that this I times internal resistance, so that I times internal resistance is called VI or V lost. I just like the word lost. You can write in the exam VI, but for the explanation purposes, this V lost to help you understand that is energy per Coulomb. That is potential difference lost for the external circuit. So the battery used that energy per Coulomb for itself. So therefore it is V lost for the external circuit. So please remember also that formula. And the only way to really train yourself on solving circuits is really to do a few examples. And if you have time in the next following days, solve a few circuit diagrams to get into the way of solving those type of questions. Then the formulas for power is also important in electric circuits, because I'm sure you have been looking at previous exam papers, and sometimes they give the information about the circuit, some of the information by means of the power generated by some device in the circuit, some kind of a resistor in the circuit. So it's very important that this power values can be given to you in an electric circuit, and then these three formulas given on your data sheet, I've copied from the data sheet. So these formulas, and I'm speaking about this last three actually, these three formulas you must use. Say for instance they give you the power of generated by a certain heating resistor, then and maybe the potential difference, you can calculate the potential difference, or the potential difference is given, then you can calculate the current through that specific resistor. So please keep this formulas for power also in mind when they give that information to you in solving a circuit diagram. In general, power relates, for instance, to brightness, and it is maybe not specifically relevant here, but maybe in multiple choice questions. Remember, the brighter a light is burning, the higher the power is. So if the power drops, the brightness of the bulb will drop. So maybe that can be of some help to you. Now, internal resistance of a battery, that is nothing else than an extra resistor in series, and you must just see it as an extra resistor as part of your series circuit. So, and you must at the end add it to the total resistance, and that is what anyway your formula is indicating to you on the showing previously to you. Now, the internal resistance causes V loss. The fact that that battery has a resistance, energy is used to move the current through energy per Coulomb charge moving through the battery is used. So there's a loss of in the potential difference available to the rest of the circuit. So therefore, V loss can be influenced and can be changed if conditions in the circuit change. V lost or VI equals I times RI. Immediately you see that this current in a circuit, has a big influence on the V lost or the VI. So many a times they give you questions where there's a change in the current in the circuit, and now you must give answers on what influence will that change in current have on the circuit, the external potential difference, etc. So remember, current determines V lost. If there's a change in current, there's a change in V lost. Now, what is the simplest way of changing a current in a resistor? You can't change the battery or the cell, otherwise you have a new circuit, a new scenario. So the best way of changing the current in the circuit is changing your resistors in parallel or series. For example, if you add a resistor in parallel, what now will the influence be? The question will be, what will the influence be on V external? So now you must go to the process of determining what is the influence of the addition of a resistor in parallel. So firstly, you must know, like I've said previously, addition of resistors in parallel will decrease R total. In the same way, if you remove a resistor in parallel, the total resistance will increase. So it's working both ways. So have a look on the question. It can be vice versa. It can be not addition, but that you disconnect by means of a switch a resistor in parallel, and then R2 will increase. But my example now is you add a resistor in parallel, then the total resistance will drop, will decrease, and if the total resistance decrease in the circuit, the total current will increase. That's very important. It is not just the resistance that will decrease, because there's a lot of resistors with a resistance in a circle. It is about the total resistance that decrease. And the very important fact, therefore, the total current in the circuit, not just the current in a certain branch, etc., but the total current will now increase. Why is the total current and the total resistance important? Because it is the total current that flows through the battery. So it's the total current that determines V lost or VI. So if IT increases, then going back to this formula, it shows you that V lost must also then increase. And what will the result be? V external. The voltage available to the external circuit will decrease. And therefore, if you have maybe a bulb in your circuit, the brightness of that bulb will decrease. The brightness will decrease. So, addition of parallel resistors is bad for your circuit in sense that it increases the current, V lost becomes bigger, and you have less energy per Coulomb for the external circuit. So your V external is less. So if you have bulbs in your circuit, the brightness will drop. So that is one of the disadvantages of parallel resistors if you use a battery where internal resistance is present. Just there were questions in the September 2019 question paper on a question where about multiplex, and you know we use multiplex very often in our houses. Now you must remember that the multiplex in your house works with alternating current. So there's no internal resistance present in alternating current. So if you add set a kettle or a toaster or something to such a multiplug. So when you add a resistor to that circuit of the multiplug, now the total resistance decreases, and the current drawn to that multiplug will increases, and then you will know that increase in total current will generate more heating energy, and therefore also more heating energy. The power dissipated then in that multiplug by means of heat energy generated per second will cause that plug to overheat. So with multiplugs, there's no internal resistance. It's only a case that the total current increases when you decrease the when you increase the number of plugs to that multiplug. You increase the number of components, electric devices to that plug. Then you decrease the total resistance, you increase the current, and more heat energy is generated in that multiplug, and that can cause overheating. Right. Now, internal resistance is also a question where the practical part of your work, you will remember you have done an experiment in the first term on internal resistance. And therefore, one of the questions in the paper must always have a practical kind of component, and often internal resistance is that question that they use to include something with a practical component. Now, the formula that includes internal resistance is this formula that I've indicated to you. And that formula relates to a straight line graph. Now, you must, if I have a look, and I think this example, if I'm not mistaken, it can be November 2018 or 2019, they've given you this graph of resistance against 1 over the current, the total, sorry for the Afrikaans, but 1 over the total current. So now you must rewrite this formula for internal resistance, including internal resistance. You must rewrite it for this graph, and it is a straight line, so it must relate to this formula y equals mx plus c. So now you realize they've given you the resistance in the circuit, so the y value must be the resistance. The x value, the independent variable, is 1 over I. So there you will see that my x value is 1 over I. And now you will realize if I rewrite then this formula into this form, then you will see that R relates to this point C. So this y junction here, this value here on the y-axis is actually then the value for your internal resistance. And then you will see the M value is the value of the EMF. So now if they ask you to calculate the EMF of the battery, now you know that you must calculate the gradient of the graph. You must calculate the gradient of the graph, and so you can solve this difficult question. But the key issue here is that you must rewrite this formula according to the graph given with your y, your dependent variable and your independent variable, your y and your x value, rewrite this formula, and then looking at that rewritten formula, you can determine what value on the graph is your internal resistance, what value on the graph is your EMF. So it is a more difficult, higher level of question, but maybe look at this type of graphs relating to internal resistance. Right, I've just indicated here that the gradient is the EMF, sorry for that Afrikaans there, and then your y-intercept here is the internal resistance, and if you must also be able to read this graph and see that this value then is 3. Although it is -3, a value of -3, you know you're working with scalar quantities and the resistance can't be minus. So although it is on the graph -3, you only write the internal resistance as 3 ohm. Now, also in one of the papers, I think maybe, I'm not sure, but I think maybe it was a paper on maybe a supplementary exam of 2018. They have given you this graph. They have given you this graph of potential difference against current. Now, what they have done here, they have increased the current, and look what effect it have on V external. And how can they, in what way are you able to increase the current in your circuit without changing your batteries? But because you can't do that, then it isn't a valid experiment. You can increase the current by working with your resistors, by adding or removing parallel resistors. So when adding parallel resistance, you will increase the current. And now they've noticed that the V external has dropped from 0 when there was no current. The value of the external potential difference has dropped. So what does this clearly indicate? This indicates the lost volts. When a current increases in the circuit due to internal resistance, the lost volts increases. So now in this graph, you must realize that, say for instance, at the circuit at a certain current value, say for instance here it is 1,123, say at a current value of 1 amperes, then you can derive this value of 0,65, and now you realize when the current value of the current is 1 ampere, you have a drop from 1,5 to 0,65. So you can determine delta V, and that delta V is V lost, and now you will realize V lost over I certainly equals internal resistance. So that's another type of question, practical question that they can ask about internal resistance. Right, that is my comments on electric circuits. I think we are going to maybe, I'm just looking at my manager, I think we're going to take a break, and I think the next topic, because I won't be able to conclude it in the time available, I have a session on just later on, so I think I will start with the next topic in our next session. So thank you very much for listening to this presentation, and I hope it has given you some direction and some valuable hints. Thank you very much.